of the KiloPower project. And what we will have demonstrated is that we can build this reactor. It works like we said it did. In particular, one of the things we're going to show is this reactor will load follow, meaning that whatever the Stirling engines want for power, the reactor will deliver that. And it does that through a simple thing called a negative temperature feedback coefficient. And that's a fancy way of saying that when the Stirling engine wants more energy, say we change the stroke on the piston, it will make the reactor a little cooler. The reactor core will get a little smaller, less neutrons leak out, the activity goes up, and power increases. Conversely, if we were to lose the Stirling engine, because we have 8 of those, then the reactor would get a little hotter, the reactor gets a little bigger in size, we only got a few more neutrons, the activity goes down, and again, the reactor will come back to equilibrium. And this is nice because we don't really have a really complicated control system. This whole reactor really just has a on-off button. And beyond that, it will start up and do its thing. I'm going to go a little bit of history. It's not that this is unique to Alamos. We've been doing this for decades. Most of you know, if you've been down to White Rock and you saw Rover Avenue, that was named after the Rover project, where the lab spent about 15 years trying to develop a thermonuclear rocket for NASA. We've had space reactor concepts going back to the 60s. We've done this off and on, a lot of times with not very much success. So we did take a different approach this time. First of all, we got some of the deal we got away, and we did some other things. But in essence, we decided to make it more like you would think of a startup. We tried to think of ways to make this a very economic project. We could do it for a very low amount of money, orders of magnitude less than what we thought we could do, so that we could keep it in the right budget frame and actually make something happen, deliver real product, not slides, but actually build a real reactor. So again, it's been part of Los Alamos' history for a long time, and we've gotten great support from all of the good lab organizations that have worked on this and worked together. In the final minute or two here, I want to make sure I've got a little bit of time. I'll touch on reactor safety because that's one of the first questions people ask is, well, if you're going to launch a nuclear reactor on a rocket, is that not like putting Chernobyl in space? Let me tell you why it's not. So that before you turn a reactor on, it has only a minor amount of radioactivity. And these little reactors have about 1 to 2 curies of radioactivity in them, which is not very much. When we launch it on a reactor and it's not turned on, if something bad were to happen, we're really not going to harm anyone. Our doses will be like at a kilometer in the millirem range. And to put that in context, you get about 300 millirems just living in the U.S. If you live in Los Alamos, it's probably a lot more because of our elevation. And in addition, if you get on a cross-country flight, you're going to get tens of millirems. And this is going to be sub-millirem. It's going to be microrem. So there's really there's not much danger if something bad happens to the reactor on a launch accident. And we're not going to turn the reactor on until we're deep in space, either headed out toward the planet or headed, we're doing something like we've landed it. So the one thing I just realized I didn't tell you we were going to do is, what does NASA plan to do with it? So right now NASA has 3 ideas of things they might want to do with a reactor. So let's talk deep space first. If you remember, we went to Pluto with the New Horizons mission, and it was a flyby. If we had a 10 kilowatt reactor and 2 ion thrusters, about halfway to Pluto, we would turn the thing around and we would start to slow down, and that would be enough energy so that by the time we got to Pluto, we wouldn't go whizzing by, we would actually try to go into orbit. So we could have an orbiter as opposed to just a flyby, and then it would get us more science. The other option is, if we go to Mars, astronauts are going to need power. And here's why. If you guys have seen The Martian, you remember at the very end of it, there was a thing that he had to strip down all the stuff off of that he needed to get from the Martian surface up to orbit. And that was called the Mars Ascent Vehicle. NASA really does have those. They are really building those. They require 28,000 kilograms of oxygen in order to be able to get off the Martian surface, and you can't bring that with you. So what you need about 40 kilowatts. So we plan on sending up 5 of these little reactors. And what they're going to do is they're going to take CO2 out of the atmosphere, and they will be used in a chemical process to make liquid oxygen. And we have to store that. And so the Mars Ascent Vehicle has to be fully fueled before the astronauts even get there. Once the astronauts arrive, they have to have power to live. They have to make oxygen to live. We have to purify their water. In addition, we have to power their rovers and all kinds of other things. And for that, we need all this power. And so that's a prime reason that NASA's interested. What may currently happen, just because of our new administration, is the moon's back on the dock. It's something that we're going to do. So as a demonstration mission, we may end up flying to the moon. There, they would either put us at the equator, because you get what's called a 2-week lunar night where you get no sun. And so the idea is to show that the reactor could power little rovers during that time. A more interesting one from a science perspective is they have these craters at the North and South Pole. They're thinking of landing a reactor in the crater. They think there may be liquid water, or not liquid water, but frozen water there that we could liquefy. And so they may actually drop the reactor and lander into the crater where there's actually no sunlight. So these are some of the things that NASA's been thinking about. Right now I just need them to get money and congressional support to do that. But again, kind of where we're at in the project is for the last 3.5 years, are trying to show that we could actually build and test this reactor and it would actually do what we said. And with that, I know I've rambled here. I've gone just about 15 minutes, but I want to give you guys a chance to have a conversation and questions.
That was perfect.
Question. Current status, you have built and tested?
So our current status, we've built a real reactor. It is in the Nevada test site. It's in a building called the Device Assembly Facility, which also is the name of that side of it is called the National Criticality Experiments Research Center. If you've been at the lab, it's really T18. That's really what it is. But we have it out there. It is up on a test stand called Comet. It is fuelly fueled. We have been running low temperature experiments up to